Hi, so now we are going to start with the theory of matrices. First of all, what's the definition of matrices? Rectangular array of mn elements enclosed in a pair of brackets is a matrix. Here, A equal to A11, A12, so on, A11, A1n, and then here in each column you have A11, A21, and so on up till AM1. So A is equal to A small a ij, where j is less than n and greater than 1. Similarly, where I is less than m and greater than or equal to 1, which represents the number of rows, and here j represents the number of columns. Now, we'll just know the different types of matrices. A row matrix. This has a single row 1 by n, a, b, c, d, e, f. So this just has a single row of elements. A column matrix is a matrix which has a single column, and it could be represented as m into n, p, q, r. Then the zero or null matrix. Here all the entries are zeros in the matrix. And then the horizontal matrix, where n is greater than m. That is, the number of rows is less than the number of columns. The number of columns is greater than the number of rows. Then the vertical matrix. Here the number of rows is greater than the number of columns. Then the squared matrix. Here the number of rows is equal to the number of columns. This will be the matrix which we will be working mostly on. Then we have a diagonal matrix. A diagonal matrix is a square matrix, that is m equal to n, the number of rows is equal to number of columns, and aij is equal to 0 for all I not equal to 0. That is, only the main diagonal elements have numbers which are non-zeros. All the other elements are zeros. Then the scalar matrix. A scalar matrix is a diagonal matrix, that is, it's a square matrix, and then all its elements which are not in the diagonal are zeros, where aij is equal to 0 for all I not equal to j. That is, all these elements are zeros, and all the elements in the diagonal, that is the diagonal matrix elements, have to be the same number. That is, aij equal to lambda for all I equal to j. And then unit or identity matrix. A scalar matrix where lambda is equal to 1. That is, aij equal to 0 for all I not equal to j, and aij equal to 1 for all I equal to I. That is, the diagonal elements have to be same. Now let's move on to upper triangular matrix. The upper triangular matrix is a matrix where if m equal to n and aij is equal to 0 for all I greater than j. That is, all these elements have to be zeros. And then the lower triangular matrix. In the lower triangular matrix, all the elements below the diagonal have to be zeros. That's the lower triangular matrix. If a matrix is either lower or upper triangular matrix, then it is called a triangular matrix. Now the addition of matrices. If a matrix goes like this, A1, B1, C1, D1, E1, F1, then we just add the corresponding elements and we get a matrix like this. A1 plus A2, B1 plus B2, C1 plus C2, D1 plus D2 goes here, E1 plus E2 goes here, and F1 plus F2 goes here. That means they must be of the same order. Properties. A plus B is equal to B plus A. That's a commutative property. A plus B plus C is equal to A plus B plus C. Associative. A plus 0 is equal to 0 plus A equal to A. Additive property of 0. And A plus minus A is equal to 0. So the addition of matrices follows commutative, associative, and additive property of 0. Then the scalar multiplication. Whenever we multiply a scalar with a matrix, we just multiply every element of the matrix by the scalar. So alpha plus beta into A gives alpha A plus beta A. Alpha beta into A equals alpha into beta of A. Then alpha of A plus B is equal to alpha A plus alpha B. Matrix multiplication. Two matrices A and B are comparable for the product only if n is equal to r. That is, the number of columns of A is equal columns of A is equal to the number of rows of B. Cij m into s is equal to A I1 B 1j plus A I2 plus B 2j, so on. So I is greater than or equal to 1 and less than or equal to m, and j is less than or equal to s and greater than or equal to 1. Now the properties of matrix multiplication. AB into C is equal to A into BC. It is associative. A into IN equal to IM into A is equal to A. It follows the identity property. K into AB is equal to KA into B. Here K is a scalar, so we are just multiplying a scalar with the matrix AB. So that will be equal to multiplying the scalar with A and then multiplying that matrix with B. A power m into A power n is equal to A power m plus n. A power m whole of n is equal to A power mn. And A inverse BA whole power m is equal to A inverse B power ma, where A is invertible. Now A power minus m can also be written as A inverse whole to the power m. Matrix multiplication is not always necessarily commutative. That is, AB is not always equal to BA. It can be equal to BA, but then we cannot be sure that it is always equal to BA. Now, the transpose of a matrix. If A is equal to Aij m cross n, then A transpose, which can be represented as A bar or A bar T, that is A transpose, is equal to Bij n into m, where all the rows of A have been transposed as the columns of B. That is, Bij is equal to Aj, where A and for all I and j. Now the properties of a transpose of matrix. A plus B whole transpose will be written as A transpose plus B transpose. Alpha into A transpose can be written as alpha into A, that is multiplied by A and then transpose. AB whole transpose can be written as B transpose into A transpose. This is the reversal law and we'll be using this a lot of times. If A is invertible, then A inverse ka transpose, which is equal to A transpose inverse. Now adjoint and inverse of a matrix. If A is equal to small aij is a square matrix, then adjoint of A is defined to be the matrix adjoint to A Bij, where Bij is equal to capital Ji, where Aj is the cofactor of the jith element of A. That means jth row ith column element of A. Now the properties of adjoint matrix. A into adjoint A is equal to adjoint of A into A, that is equal to determinant of A into identity matrix of the same order. Adjoint into alpha of A is equal to K power n minus 1 into adjoint of A. This is a very important property and we are gonna use this a lot of times. Alpha into AB is equal to adjoint B into adjoint A. This is similar to the reversal law which we just learnt in the inverses. Now, singular matrix. Singular matrix is a matrix whose determinant is 0, that is determinant of A is equal to 0. And a non-singular matrix is a matrix which is just non-singular, that is whose determinant is not equal to 0. Inverse of a matrix. It is AB is equal to BA is equal to I, then B equal to A inverse. And the inverse of a matrix exists only if a matrix is non-singular, that is det is not equal to 0. A inverse is equal to 1 by det A into adjoint of A. That is why if A is not 0, only then the inverse of A exists. Now the properties of inverse of A. A into A inverse is equal to A inverse into A is equal to In. A inverse ka whole inverse will be just A. And K into A inverse can also be written as Ka whole inverse if K is not equal to 0. And AB whole inverse is written as B inverse into A inverse. This is similar to the reversal law. Now we'll get to know a little more of matrices. Symmetric matrix is a matrix where A is equal to A inverse. Skew symmetric matrix is a matrix where A inverse is equal to minus A. Now Hermitian matrix. Hermitian matrix is a matrix where A is equal to A conjugate. That is, here A star is the complex conjugate of A. Now skew symmetric matrix. Skew symmetric matrix is a matrix where A conjugate is equal to minus A. Orthogonal matrix. Orthogonal matrix is a matrix where A into A transpose is equal to A transpose into A is equal to I, and A transpose is equal to A inverse, because this law actually was A into A inverse is equal to A inverse into A is equal to I. But now we are writing it as A into A transpose is equal to A transpose into A, that is A inverse is equal to A transpose. That is the det of A is equal to plus or minus 1. Unitary matrix. Unitary matrix is a matrix where A into A conjugate is equal to I. Nilpotent matrix. If there exists a positive number m such that A power m is equal to 0, then it's called a nilpotent matrix. Involutory matrix. A square is equal to I, then it's called an involutory matrix. Trace of A. Trace of A is the sum of all the main diagonal elements in a matrix. That is, all these elements in the matrix. So it has to be a square matrix. System of linear equations. a11 x1 plus a12 x2 so on a1n xn is equal to b1. So on we have m similar equations. Then these can be written like this. See, the coordinates of x1 are all written in the same row, same column, and then the coordinates of x2 in the same column again. So we have m equations, so m rows, and n like n unknowns, so n columns, into x1 x2 so on xm is equal to b1 b2 so on bm. So ax is equal to b. So a is the coefficient matrix, x is the unknowns, and b is the result matrix. An augmented matrix A by B is this matrix plus this matrix written side by side. So a11 a2 a12 so on, this is the coefficient matrix, and then this is the result matrix. This is called an augmented matrix, which we are going to use a lot of times. Now we come to the last part of the theory. If ax is equal to b, this is the matrix we have got. Then b equal to 0 or b not equal to 0 are two cases. If a is not equal, determinant of a is not equal to 0, then this system of equations has a trivial solution. And if the determinant of a is equal to 0, then we get an infinite solution. Now, if the rank of matrix A is equal to the rank of augmented matrix AB, then the system is called as consistent. Now, rank of A, if it is not equal to the rank of augmented matrix AB, then the system is known to be inconsistent. You will need to memorize this tree because we will be using this a lot of times in all the systems of equations. And the system of equations are always simpler to solve when we are using matrices. Case 1. If the system is consistent and m is greater than or equal to n, then if row of A, that is the rank of A, is equal to the rank of augmented matrix AB, which is equal to n, then the system has unique solution and m minus n solutions are superfluous. If the rank of A is equal to the rank of augmented matrix AB and which is equal to r less than n, then n minus r unknowns are unknowns, and r can be found in terms of these arbitrary values assigned to these n minus r unknowns. If m is less than n and these are consistent equations, then if the rank of A is equal to the rank of augmented matrix AB, which is equal to m, then n minus m are unknowns. The remaining can be found in terms of the arbitrary values assigned to these values. If the rank of A is equal to rank of AB, that is the augmented matrix, which is equal to r and less than m, that is the number of columns, then n minus r values are unknowns, and the remaining values can be found in terms of the arbitrary values assigned to these n minus r values. To find inverse of A, we begin with AIN. That means we write the matrix A, and then we write the matrix this, if this is a 3 by 3 matrix, and then we convert it into something like this. If it gets converted into this and we have a matrix here, then this matrix, this part of the matrix is A inverse. That's it.